All right, everyone. Let's start our first session. Good morning, dear friends. Good morning, dear presenters and listeners. And it's a pleasure to open the first session of this conference and to invite our first presenter, Professor Piotr Piecuch from Michigan State University, who will tell us about a very interesting topic of exact quantum chemistry by semi-stochastic and selected CI, which is presently a very hot topic in quantum chemistry. So, dear Piotr, please, the floor is yours.
Okay, so I have to share screen, right?
Yes.
So let me open the talk first.
That'd be terribly nice.
Yep. And share screen. Okay, can you see my screen now?
Yes.
Okay, good. So let's see, let me move this. Well, maybe I can minimize this, I think this way. Okay, so let me fix my pointer. Okay, so I think we're good to go. Okay, so thank you very much, Michael. Let me first say good morning to all of you on Jeju Island, and I guess those of you who are far from Korea in a different time zone, it's probably, I should say, good afternoon or good evening. For me, it's an evening. I'd like to begin by thanking the organizers for the invitation. This is my second meeting in the series New Horizons in Scientific Software. Last year, I talked about more of our application projects where we used our methods to describe the photochemistry of the photoactivated superbase, which is called FR0SB, which was synthesized in our department. This year, I'll spend time on discussing some methodological advances in electronic structure theory, trying to tell you a little bit about how we can approach the exact or nearly exact quantum chemistry by combining the stochastic quantum Monte Carlo methods and selected CI that Michael mentioned with Kappa cluster computations. So much of this talk will be based on the concepts of the single reference Kappa cluster theory. So let me first briefly review those. Here's the wave function ansatz of the single reference Kappa cluster theory. We obtain the ground state wave function by applying the exponential operator e to the t to the reference determinant phi, which in this talk will always be a restricted Hartree-Fock or restricted open shell Hartree-Fock determinant. Of course, we can make other choices. T is the cluster operator, which we typically write as the sum of various many-body contributions. The one-body contribution T1 that describes one electron excitations, T2 describes doubles, T3 triples, and so on. And here's the well-known hierarchy. Okay, what's happening? Of Kappa cluster approximations obtained by truncating the many-body expansion of the cluster operator at a given excitation rank. So the leading approximation is called CCSD, where T is truncated at T2, the two-body term T2. The next one is CCSDT, where you truncate the cluster operator at three-body component T3. The next one is CCSDTQ, where we truncate T at T4, and so on and so forth. And here are the equations that we, let me see if I can remove that. Okay, also this one. And here is are the equations that we solve in single reference Kappa cluster methods. They are obtained by projecting the Schrödinger equation of the Kappa cluster wave function on the excited Slater determinants that correspond to the content of the cluster operator. And once we solve this nonlinear system of amplitude equations, we determine the energy by projecting the Schrödinger equation on the reference determinant phi. Now, Kappa cluster methods have several advantages. For example, one of the most prominent ones is size extensivity of the resulting approximations. But in this talk, the feature which is particularly relevant is the very fast convergence of the Kappa cluster approximations toward the exact full configuration interaction, full CI limit. Typically, by the time we reach high levels such as CCSDT or CCSDTQ, we are virtually converged with respect to the man-electron correlation effects. This is not only actually true for weakly correlated systems, as it is sometimes said, this is also true for systems which we typically call multi-reference, such as single and double bond breaking, biradicals, things of that sort. The only time where kappa cluster methods will fail is the strongly correlated regime characterized by the entanglement of a large number of electrons. When we entangle a few electrons, that's not a problem. So one of the key challenges in kappa cluster theory has been how to incorporate higher than two-body components of the cluster operator and excitation operators in the case of equation of motion kappa cluster that are needed for a quantitative description without running into prohibitive computational costs of higher order methods such as CCSDT or higher. The traditional solution, as you all know, has been to use various perturbative approximations such as the popular CCSD parenthesis T, triples correction to CCSD, and methods like this, of course, help a great deal. They are much less expensive than their full CCSDT and higher parents, but they are not robust. As you can see, we cannot describe bond breaking, we cannot describe biradicals, we cannot actually even describe systems which are characterized by very large dynamical correlations. This has been a problem. And this problem can be attacked in multiple ways. I will focus on one specific way today, namely the idea of moment expansions. And I'll talk about the so-called CCPQ moment expansions to be more specific. So what are these moment expansions? These are methods which are essentially based on a straightforward idea of correcting the lower order kappa cluster calculations for the higher man-electron correlation effects. In the case of CCPQ, we start by defining the subspace of the man-electron Hilbert space, which is spanned by the Slater determinants that dominate the wave function of interest. We solve the kappa cluster equations in that P space, and then we correct the results of the P space kappa cluster calculations for the higher order man-electron correlation effects, which can be captured with the help of another subspace of the Hilbert space, which I will call the Q space. There are equations behind all of this. You can see them here. We're not going to be reading every symbol. The most important message of these equations is that the corrections delta here are written as linear combinations of these quantities designated by m's. Those are the moments of kappa cluster equations, projections of the Schrödinger equation with the P space kappa cluster wave function in it on the excited Slater determinants from the complementary Q space. So they're not the traditional perturbative corrections, they are moment corrections. How can we use such corrections in practice? Well, we can use them in a very conventional way. Suppose I'd like to correct CCSD for triples. Well, then I will define the P space to be single and double excited determinants, the Q space, the triple excited determinants. If I follow the equations on the previous slide with these definitions, we end up with an approach called CRCC23, the completely normalized kappa cluster method with singles and doubles. That's the 2. Corrected for the triples, that's the 3. And of course, we can build a whole hierarchy of such approximations. Is another one, CRCC24, where we correct for triples and quadruples. Here's just a reminder how these methods work, how they improve situations such as bond breaking. So let's look at the F2 molecule. This is the CCSDT curve for it. It's pretty accurate, very accurate for it. It's not exact, but it's very accurate. This is CCSD, of course, not good. We need to correct it for 3-body clusters. This is what you obtain when you try to do this with CCSD parenthesis T. That's not good, obviously. And this is what CRCC23, our triples correction originating from the CCPQ moment expansions, produces. So methods like this are very practical. You can apply CRCC23 to systems with dozens or even hundreds of atoms, but that doesn't mean that they are perfect. Obviously, there are situations where they fail. Here's one example, the automatization of cyclobutadiene, where we have the sort of rearrangement of pi electron network. The interest here is in getting the activation energy right. So here I'm using CCSDT, which produces about 8 kcal per mole, which is a reasonable number compared to the best numbers that have been produced over the years. And as you can see, CRCC23 is a total failure. It's not improving parenthesis T. It produces the activation energies which are twice as high, more or less, as the result of CCSDT calculations. So what's the problem here? Well, the problem is that in corrections to CCSD, we are assuming that we can decouple the lower order clusters, in this case T1 and T2, from the higher order clusters such as T3. But of course, we know that these classes are coupled. So the question is, how can we incorporate the coupling among the cluster operators while retaining the idea of non-iterative energy corrections? Well, the CCPQ moment expansions are flexible. We can accomplish this by redefining the P and Q spaces. We can, for example, define the P space to consist of all single and double X-ray determinants and a subset of triple X-ray determinants defined via active orbitals, as in the approach called CCSD little t. The little t means selection of triples using active orbitals. And then the Q space will simply be not all triples, but the remaining triples, those which are not captured by CCSD little t. If you do all of this, you end up with an approximation which we call CC little t 3, which is in games, just like CRCC23. You can try it yourself. And again, we can always build hierarchies of approximations. So there's another one. And these methods are very accurate. You know, if I go back to this automatization of cyclobutadiene problem, where I was complaining about corrections to CCSD failing, you can see that CC little t3 reproduces the energetics of CCSDT, the parent approach, to within about 0.1 milliHartree, not just for the activation energy, but also for the total energies. So that's pretty good, except that in order to get these good results, I had to resort to active orbitals to tell the computer code eventually what kind of triples I should be putting in the P space. Well, but that's not a black box anymore. So we ask ourselves the question, can we make this process more automated? That is, can we define P spaces in a more automated fashion? And we discovered that one can do this when we help ourselves by fusing the deterministic CCPQ theory with stochastic CI or kappa cluster Monte Carlo. So in the stochastic part, I'll rely on CI and kappa cluster Monte Carlo ideas that were introduced by Ali Alavi, Alex Tom, George Booth, and co-workers. Now I'm assuming that the audience knows what quantum Monte Carlo is. Here we'll be talking about quantum Monte Carlo wave function propagations in the many electron Hilbert space. So how can we combine these Monte Carlo ideas with CCPQ? Well, here's what we can do. So here's an illustration. My example is F2, twice the equilibrium bond length, where T3 clusters have a larger energetic effect than the dissociation energy. The top panel shows you the Walker population growth. So we go from hundreds and thousands and higher and more the Walkers on various determinants. And the bottom panel shows you the convergence of the full CI quantum Monte Carlo algorithm toward full CI. This x-axis here, the iterations axis, tells you that that's essentially the time propagation axis, which is represented here by Monte Carlo iterations, which are Monte Carlo time steps. Okay, what we're going to do about this is something very straightforward. We can look at what kinds of determinants, slated determinants, the quantum Monte Carlo propagation picked up in the beginning of the propagation. We can look later or later. Obviously, as we keep looking later and later, the list of determinants picked up by Monte Carlo gets longer and longer. If you look at the second column, I'm not sure if you can read it, but anyway, some determinants are more important than others. They accumulate more Walkers, but that's not going to be very important for us. What is important is what kinds of determinants are being captured. So suppose I would like to convert CCSDT. Then I will look at that list of determinants and try to identify which ones are triply excited determinants. Those which are on the list will end up in the P space. Those which are not on the list will be incorporated through our moment corrections in the Q space. Okay, so here's the summary of what I just said. If I want to convert CCSDT, our P space will be defined as all singles and doubles and a subset of triply excited determinants which are captured by Monte Carlo. The Q space will be the remaining triples. And if I want to convert CCSDTQ, then the P space will consist of single and double excited determinants. We'll take them all, and then a subset of triples and quadruples, or triplets and quadruple excited determinants to be more accurate, that are captured by Monte Carlo. And again, the Q space is the rest of the information, the remaining triples and quadruples. So let's see how all of this works. So here's an illustration, the F2 molecule. We go from equilibrium bond length here all the way to 5 times equilibrium. So we're breaking the FF bond. The green lines here are full CI quantum Monte Carlo propagations. You can see the noise because I zoomed the energy scale. So now you can see that it's a stochastic approach. And here's what happens when we solve kappa cluster equations in the P space defined by all singles, all doubles, and a subset of triply excited determinants captured by Monte Carlo. You can see a nice convergence towards CCSDT. And we can now accelerate this convergence even further if we correct these results for the remaining triples, which are not captured by Monte Carlo, those black lines with the black squares on them. And as you can see, we have a very rapid convergence towards CCSDT out of the early stages of Monte Carlo propagations. Of course, here I'm using full CI quantum Monte Carlo. I don't have to do that. We can replace full CI quantum Monte Carlo by, say, CISDTQ Monte Carlo, where now we're not allowing spawning beyond the space of quadruples. I can even go to something as simple as CISDT Monte Carlo, where we're not allowing spawning beyond the space of triples. Obviously Monte Carlo now converges to a totally different limit, but that's not important for us because it does provide the list of triples. And if you look at these black lines with black squares on them, we are converging CCSDT rapidly. All of these examples, we're using the small basis set, CCPVDZ. We can, of course, try large basis sets. And as you can see, it doesn't matter. You can try larger basis sets and the convergence will be, again, very fast. And there are, of course, benefits, computational benefits when you do all of this, because Monte Carlo propagations in the beginning, in the early stages, are very fast. Kappa cluster calculations on a small fraction of triples, you can see those fractions, they are 10% or so, are much faster than the parent CCSDT calculations that use all triples. And then the non-iterative corrections, these moment corrections, are more or less like parenthesis t times a factor of 2 or so. Okay, so they are much less expensive than the single iteration of CCSDT. And so when I return back to our example of automatization of cyclobutadiene, where I was sort of complaining, right, that CRCC23 or parenthesis T are unable to reproduce the full CCSDT activation energy, which should be about 8 kcal per mole. CRCC23 produces 9 kcal per mole of an error. Parenthesis T, it's about 8 kcal per mole of an error. You can see that by the time we have our Monte Carlo calculation picks up about 15% of triples in the P space, and then we correct for the rest of them with our moment expansion, we end up with about a chemical accuracy regime, about kcal per mole. So that's a very nice convergence. You can see the same if you look at the individual structures, the reactant and the transition state. You just look at these black lines with black squares on them, you see this rapid convergence again. And the nice thing about it is that we're not constrained to CCSDT. We can go to higher levels of kappa cluster theory. This is CCSDTQ now. Okay, the example is the water double bond dissociation, or stretching, I should say, by a factor of 3. Okay, each bond is stretched by a factor of 3 while keeping an angle. That's a pretty difficult geometry because if you look at it here at the bottom part, CCSDT produces a 40 millihartz of an error already. Okay, you need T4 clusters to get it more or less right. Actually, you probably would like to consider even more than that, but let's stick with CCSDTQ. And if you just look at the last column and this row, 20,000, you can see that with just about 5% of triples in the P space and 1% of quadruples captured by Monte Carlo, we are already in a sub-millihartz regime compared to full CCSDTQ. Okay, and now we can use the same ideas to study excited states, because we can use equation of motion kappa cluster theory and use Monte Carlo to tell us what to put in the P space for the EOMCC runners. And then again, we can use moment corrections to correct for the remaining correlations. Okay, my example here is the CH plus system, for which we can easily do EOMCC SDT, which is actually itself essentially exact if you compare to full CI. And what I'm plotting here are errors relative to full EOMCC SDT as a function of the Monte Carlo iterations or Monte Carlo time steps. We're computing several excited states at the same time. So some of them are doubly excited, like this 2 sigma state or these 2 delta states. The rest of them are singly excited. And here you can see the pretty good convergence toward EOMCC SDT, even without the moment correction. Please look at the energy scale. It's in millihartz 3. When we add the corrections due to the missing triples, our convergence is pretty much instantaneous. This is an equilibrium geometry. We can look at the region outside the Frank-Condon region, and by stretching a bond, that's what I'm doing here, by a factor of 2. And if you look at the right panel, you can see again the same very fast convergence. Now, this is important because all these excited states for this geometry are already strongly correlated. They are all multi-reference. They are all dominated by double or even triple excitations. So it's good to see that fast convergence. We can also use other things like compute singlet triplet gaps in biradicals. This is one of the many examples we computed in one of our recent papers, cyclobutadiene at the triplet geometry. The gap should be minus 5 kcal per mole. I'm saying minus because singlet is the ground state. And again, if you just look at these panels, if you look at these dark points, the convergence is again very fast, both for the singlet triplet gap and for the individual states. So this is not some cancellation of errors situation. We are really converging the states as we should toward, in this case, the CCSDT limit. Okay. Now, so far I used quantum Monte Carlo, but we're not, of course, constrained. We could use some other sort of automated approach to generate the P spaces for us. And Michael already mentioned the selected CI. Indeed, there's been a renewed interest in selected CI approaches in recent years. So we decided to see, can we fuse CCPQ with selected CI? And for us, selected CI will be one specific approach so far, namely the SIPSI approach, the approach that is abbreviated as SIPSI. So here's are the results of our calculations for F2. So we go from equilibrium again to 5 times equilibrium. And if you look at the black lines with black squares on them, okay, you can see that we're converging CCSDT out of the earliest stages, you might say, of the SIPSI wave function propagations. That is, with just thousands of determinants in the SIPSI spaces, we can essentially converge CCSDT. And this is more of the same. If you just look at the last column, I know there are many numbers, but let's just look at the last column. Again, this is the automatization of cyclobutadiene. Okay, you can see that by the time we have about 100,000 determinants in the SIPSI diagonalization spaces, we are already within essentially chemical accuracy, about a kcal per mole relative to CCSDT. So we don't need millions. You have to realize that for this problem, CCSDT has tens of millions of triples, for example. So we don't need that much to be converged. And in the last couple of minutes, a few minutes that I have or don't have, let me just mention that we can also consider attacking the full CI problem directly without doing any sort of kappa cluster work of the CCSDT or Q type. Okay, so here's an observation. If you write the Schrödinger equation for the kappa cluster wave function, and if you do not do any approximations and look at the equations projected on the singly and doubly excited Slater determinants, then you can see that there are no cluster operators higher than T4 in the system, and that's because the Hamiltonians in quantum chemistry that we use have only two-body interactions, and for the same reason, the energy uses only T1 and T2. So what we can do about this is something as follows. If someone gives me the exact, meaning full CI values of T3 and T4, then I can solve for T1 and T2 in the presence of the exact T3 and T4. That will give me the exact T1 and T2, and that means that I obtain the exact, meaning full CI energy. That's an observation, not a practical one yet. Nevertheless, it's an interesting observation. That observation is not new. It actually already was used in the 1980s and 1990s, especially, in the form of the so-called externally corrected kappa cluster methods, where we typically used T3 and T4 extracted from non-kappa cluster wave functions such as projected UHF, or multi-reference CI, or others. But nowadays, of course, we have quantum Monte Carlo, full CI quantum Monte Carlo. So we propose the following algorithm. We start full CI quantum Monte Carlo propagation. We look at the full CI quantum Monte Carlo wave function at a given propagation time and extract the information about singly, doubly, triply, and quadruply excited amplitudes by counting the Walkers on those determinants. We perform a cluster analysis to extract T3 and T4, using the relationships between the CI and kappa cluster excitation amplitudes. We solve for T1 and T2 in the presence of T3 and T4 extracted from full CI QMC, and we know for sure that in the limit of infinite time, this will allow us to converge the exact full CI energy. The approach that I just summarized is called cluster analysis driven FCI QMC or CAD FCI QMC. And here's an illustration how it works. Again, we're looking at the double bond dissociation in water. If you look at these panels, I go from equilibrium to twice the equilibrium. The green lines are full CI quantum Monte Carlo runs, the purely stochastic ones. Of course, they do converge as you propagate along the imaginary time axis, but it takes time for, say, twice equilibrium. And red is what we obtain by solving for T1 and T2 in the presence of T3 and T4 extracted from FCI-QMC. This is more of the same in numbers. I'm not sure if we need to read all the numbers, but if you just want to look at what kinds of convergence we have in millihart-free, those are, you can look at those red numbers in the yellow field. So there is a rapid convergence toward full CI. And at the end, let me just mention that we can go with this to, for example, a strongly correlated regime. I don't have a lot of time to talk about it, so let me just mention to situations such as this H10 ring that can be used to model the transition from the metallic phase with weak correlations to an insulating phase with very strong correlations. Okay, we can still use CAD FCI-QMC. If you look at the bottom panel where I'm plotting errors relative to full CI as a function of the H-H separation, this is what the stochastic, purely stochastic FCI-QMC produces. Of course, it converges as you propagate, but it takes time to obtain the converged result. This is what we obtain when we solve for T1 and T2 in the presence of T3 and T4 and a little bit of T2 square extracted from FCI-QMC. Let me also mention that we can go way beyond what can be done with conventional full CI. This is a project that was organized by Jürgen Gauss and Janus Eriksson for several research groups where we tried to extrapolate the full CI energy of benzene in a CCPV-DZ basis set. That's the Hilbert space of about 10 to the 35 configuration state functions. This was the opportunity for my group to apply CAD FCI-QMC. And we did obtain the result, which is converged to about 0.1 millihart-3. That's the one that you see here highlighted in yellow. And what was nice about this blind challenge project is that after this project was completed, Cyrus Zummerger and co-workers and Pierre-François Luz, who is in the audience, and co-workers used their respective selected CI methodologies and obtained results which match our calculations quite well. That was very pleasing for us. And at the end, let me just mention, I will definitely not get into details, that we, just like in the case of CCPQ, we can replace Monte Carlo by CIPSI and essentially extrapolate the full CI energetics out of the relatively small CIPSI runs by using the idea of externally corrected Kappa clusters. So with all of this, let me stop. Let me thank my co-authors here, Emiliano, Ilias, Stephen, Arnab, Kartik, and Dwin, and let me thank you for your attention. Let me thank the organizers once again for the very kind invitation.
All right, thank you very much, Piotr, for a very nice lecture. And now your talk is open for discussion. So let's invite our listeners to ask questions. Any questions from the audience? All right, let me start then. You very nicely presented the idea of stochastic methodologies applied in the realm of TI and couple cluster, but don't they lead to some bumpy potential energy surfaces?
Yeah, that's an excellent question. I mean, from what our observe, we are able to converge to a level of microarteries, really, right? So that, so first of all, I mean, I had these. Let's see if I can get there. Maybe not as quickly as I would like to, but if you remember this, these plots, when I was showing some of those, for example, this one, right, or this one, you can see that the noise of Monte Carlo is largely eliminated because we resort to determinism, right? So so yes, of course, in principle, there is always a little bit, but since we're converging way below, like 0.1 millihertz is very easy to get, and we can get to microarteries, we don't see much of a consequence. But of course, I don't want to say that that it's perfect. Definitely the corrections help, because, we also have these moment corrections. So in other words, we are correcting for the missing triples. And in this way, whatever was not picked up by Monte Carlo is picked up through the corrections.
Sorry, Piotr, I can't hear you. Yeah, right. So basically you stopped, right?
Yes, I stopped right now. Yeah.
Oh, right. Yeah. Great.
Sorry, I should say that. Sorry.
Oh, yeah. Sure. So any perspectives for obtaining the energy gradient with this method, either analytical energy gradient or maybe numerical?
Well, we haven't done anything in this direction. So, of course, for analytic, that probably, may not be straightforward, I would say, because you would have to really consider, okay, may not be so bad. Maybe I should say this, but you would have to make sure that your surfaces are totally smooth, which probably would mean that you would, when you start moving atoms around, you probably would like to make sure that that this space of triples is, for example, the same, right? So that it would be something to pay attention to. We haven't done anything in this direction. Of course, that would be useful, but we're still behind, I guess.
Oh, all right. Well, thank you. And we also have a question from the audience, from Valero Viryazov.
Yes, I can read it. I can read it.
You can read it.
So
right.
the question is, I don't know if you can see it. If you still see my screen, you probably can see it. So it says that full CI is the gold standard only in connection with complete basis set. How all this scale increase basis sets from DZ? Well, okay. So essentially, when it comes to CCPQ, what I started with, they're similar to what we call these active space approaches. So the cost is, on the order of CCSD times a small prefactor, okay, more or less, which is now, of course, depends on how many, what is the fraction of triples that you have in the P space. Okay, so, but that's the cost. Monte Carlo itself is really in the early stages is very fast. So it's really a tiny fraction of the effort. And the non-iterative moment corrections are also, they are essentially n to the 7 scaling of parentheses t. Okay, but as we know nowadays, I can do this for systems with dozens or even hundreds of atoms if we use local metals, for example, right? So that's that is pretty practical. When it, but I'm not saying it's as it's not certainly not density functional theory type accuracy scaling. Nevertheless, it's already practically enough. Now, when it comes to this last part, the external collected kappa cluster, the cost of it is essentially the cost of performing full CI/QMC for a given propagation time, and then you have to, so that's this last part that I discussed, and then you have to perform essentially the CCSD calculations. So I can even give you timings for benzene, so that because that I remember. So in this case, so when we talk about this benzene project, we're actually working at that time closely with Ali Alavi, because we wanted to use his unpublished yet version of NISI. Okay, previously we used Handy, which is available, and he needed about for benzene to get the wave function reasonably well converged with about, I think it was 2 billion walkers. He needed essentially overnight on a few hundred nodes. Okay, so it wasn't a cheap Monte Carlo, but the purpose of that Monte Carlo was to really get it tightly converged. Then our cluster analysis took a couple of hours on a single core of a small PC. Okay, and then the kappa cluster run was 10 seconds or something like that. Less than a minute for sure. It was really fast. So we can do something which gives you full CI level accuracy to within about 0.1 milliHz for systems like benzene. I'm not saying that we can do it for everything, because of course, eventually, if you cannot do full CI Monte Carlo, of course, then we're stuck, right? But we certainly can go what is currently possible with full CI.
All right. Thank you very much, Piotr. In view of the time, I have to close the discussion.
Okay, so I'll stop sharing now.
Yeah, and let's thank Piotr for his excellent lecture. And it's my pleasure to invite our next speaker,